I'm going to present the computational fluid dynamics. We are from Group A, which is led by Eric, members Lawiki, Kai, and Joshua. Eric is going to run the simulation, video of the method, and discussion of the result. Lawiki is going to do the introduction and theory, while the discussion of result and video editing are done by Kai and Joshua. The topic of the assignment is M to simulate and analyze fluid flow over a flat plate using fluent computational fluid dynamics. Theoretically, the flow of fluid can be described by Navier-Stokes equations. The Navier-Stokes equations are vector partial differential equations that include the main properties in fluid flow such as velocity, viscosity, density, temperature, and pressure. Thus, the equations flow conservations of mass, momentum, and energy, which is very useful in analysis. And in this study, we do simplify analytical calculations by ignoring and marking assumptions to some fluid properties. Numerical analysis could provide more precise results for fluid flow, but it is more complex in calculations. Nowadays, we have computers to simulate flow of fluid and aid us to analyze it numerically. By the help of Fluent CFD, we just need to provide the certain data to generate a quite accurate flow simulation. The main objective of this assignment is to simulate and analyze a laminar airflow over a flat plate using analysis fluent. Create contour and XY plots to see the velocity boundary layer form. Evaluate how changing airflow velocity affects the boundary layer. And we have two cases, which is 1 meter per second and 1.5 meter per second. Here we come the method of the simulation. By comparing the two images, the boundary layer for the 1.5 meter per second flow at the right side is visibly thinner than for the 1.0 meter per second flow at the left side. This visual evidence directly confirms that increasing the airflow velocity reduces the thickness of the boundary layer, which was a key objective of this simulation. These are velocity vector plots. Each arrow shows the direction and speed of the air at that specific point. Longer arrows mean higher velocity. This visualization shows the velocity profile of the boundary layer. You can see the arrows are very short, near zero speed at the plate's surface and get progressively longer as the distance from the plate increases. When comparing the two, you can see the transition from short arrows to long arrows happens over a shorter vertical distance in the 1.5 meter per second case. This visually confirms that the faster flow has a steeper velocity gradient and a thinner boundary layer. The profile for the 1.5 meter per second case reaches its maximum velocity at a lower height compared to the 1.0 meter per second case. This is the definite proof that the boundary layer is thinner and the velocity gradient is steeper for the higher velocity flow. That's all from us. Thank you.